Hello, everyone. Thank you for joining my seventh talk in the Science and Religion series. So, as you can see, this talk is on the Earth. If you're just joining in, you do not necessarily have to watch my talks in order. However, this one is kind of a continuation of talk 5 and 6. So, I'll do just a brief introduction to that. So, talk 5 was on the Copernican principle. And the Copernican principle is the principle of mediocrity, which says our universe, our solar system, our Earth, our planet, everything is not unique. So there's nothing special about where we live and how everything existed. So the last talk, lecture 6, we looked at our universe, our galaxy, and our solar system, and kind of looked at where we're located and is it unique or not. And so this talk is a kind of a continuation, but we're specifically going to look at our Earth and our moon. So looking a little bit closer at home. So we started off kind of bigger and now we're kind of getting closer. Also, I forgot to introduce myself. My name is Dr. Christina Sweeney Hillesheim. And so, yeah, let's jump in. So, before we start with the Earth, first let's talk about the moon. So here's a nice picture of the moon from NASA. And just to give you some little facts about the moon is 250,000 miles from Earth. So it may seem like it's very close whenever you're looking outside at night or something, but it's actually pretty far away. So around 238,000 miles, or if you prefer a different system, 384 kilometers. Now, it does differ due to the moon's elliptical orbit. So, what that means is sometimes it'll be slightly closer to the Earth and sometimes it'll be slightly further away. So, that's why we have about an average of the distance there. Now, why is the moon important? Is it good to have the moon? Does the moon benefit the Earth at all, especially when it comes to having life on Earth? So the moon actually stabilizes the tilt of the Earth's axis. So talking about instead of it being directly up and down, we have a little tilt on our Earth. So our North Pole and South Pole aren't directly up and down, it's tilted. And the moon stabilizes this tilt. And our seasons are actually due to the tilt of the Earth's axis. So how we can think about this is if we have the sun here, and this is the Earth, so I'll do it kind of like this so you can see the tilt. So during the summer, the northern hemisphere, the North Pole axis is going to be pointed toward the sun. So you're going to get a little more hotter weather. And then 6 months later, the Earth, when it comes on the other side of the sun, now the South Pole is going to be located closer. And then you'll have summer in the South Pole. This is also why, if you didn't know, but the northern hemisphere and the southern hemisphere have different seasons. So you may be, if you're used to living in the northern hemisphere, you might be used to having Christmas be a cold kind of holiday. Whereas if you're in the southern hemisphere, think maybe South Africa, Australia, they have warm Christmas. And that's due to the tilt of our Earth. Now, it's actually good to have this tilt because if we had too much or too little, our seasons wouldn't be as mild. So this is one of the reasons that we actually have very mild seasons. Now, how much is this tilt? I was kind of being a little more dramatic when I was comparing it with the sun, just so you could see it on the screen. But the Earth actually tilts at 23.5 degrees. And you might say, okay, 23.5, that's a little hard for you to kind of imagine. But the most interesting part is that it actually varies by only 1.5 degrees. So the stability of this tilt is because of the gravity from the moon's orbit. So the moon helps to keep our tilt on Earth consistent within that 1.5 degree range. Now, you might say, well, what would happen without the moon? So without the moon, our tilt would be very chaotic. We could even have up to a 90-degree difference. Now you might say, okay, well, what would happen with that? So let's go back to our analogy. Here's the sun. Now, if we had a 90-degree, and this is the North Pole would be exposed to the sun for 6 months. So really, really long summer. And then when we come around, then it would be Down the South Pole would be exposed, but the North Pole would be dark. So our seasons would be much more chaotic, much more different. Excuse me. Now, this is actually unique in the inner solar system because Mercury and Venus actually have no moons, and Mars has two tiny moons, which were probably captured asteroids, but they don't do anything to stabilize the axis of Mars. So all three of these planets have chaotic variations in their tilt. So Earth is lucky to have the moon because it stabilizes that tilt and allows for more milder and more reasonable temperatures on our surface. So what else is interesting about the moon? So the other things that the moon does is it actually increases our tides. So the moon contributes 60% and the sun contributes another 40% to our tides. So that's the flow of water associated with our coast going in and out. So why are tides important? So this movement of water actually keeps the flushing of nutrients from the continents to the oceans going. And we'll talk about this a little bit more. But this water, when it flows onto the continents, will collect nutrients and then bring them back into the ocean. So having this tide keeps this kind of flushing of the nutrients into the ocean. Additionally, the tides circulate the heat that is absorbed by the oceans. If the water wasn't really moving and was stationary, we wouldn't get that circulation that happens due to the tides. But what if the moon were larger? So say our moon was just a little bit larger. What would happen? So one of the side effects of our moon being larger would be that the tides would be too strong. And so what does that mean exactly? So what happens is with the tides actually pull on the Earth and actually slows it down. It slows down our rotation. And interesting, as the moon is pulling, as the gravity of the moon is pulling onto our Earth and kind of having stronger tides and slowing down the Earth's rotation, the moon is actually also moving away. So it's doing two things at the same time. So it's slowing down the Earth's rotation and moving away from us. So if it were larger, it would do this to a more extreme case. Right now, the moon is actually moving away from us 3.82 centimeters a year. So a very, very small amount, and it is slowing down the rotation, but it's doing it in a very, very kind of such a small amount that we don't even notice. But if the moon were larger, that distance would be greater and the slowing down of the rotation would be even larger. Now, what would happen if we were to have a slower rotation? What would happen would be that the days would become a lot longer. So our temperatures would be more extreme. We'd have very large temperature differences between our days and our nights. So we would have hotter days, colder nights, depending on if the tilt, which also would be affected by the size of the moon and the distance the moon would be from Earth. All right, so now that's kind of the moon. So now let's focus a little bit more on Earth specifically. Is there anything unique or necessary for our Earth? So to give you some facts about Earth, Earth is about 8,000 miles in diameter. So about 12,700 kilometers. So diameter would be if we're talking about kind of like going across it. And at the center, you could kind of see this in this picture. It's not super accurate, but you could kind of see that at the center is going to be a solid iron core, and it's surrounded by iron that has been rendered liquid by the heat. So due to the heat and due to the pressure and due to the temperature, that iron is going to be in liquid form, surrounding that more solid solid iron core. So like I said, at its center, the pressure is more than 3 million times greater than that at the planet's surface, which is good for us because if it was that high pressure at the surface, we wouldn't be able to survive. So there's a big differentiation between the pressure at the center of the Earth and the pressure on the surface of the Earth. Also, the temperatures in the center of the Earth can rise up to 9,000 Fahrenheit or 5,000 degrees Celsius. So Also something that we just definitely don't want to have on our surface. So we have a very hot, pressurized core for our Earth. Now, you may say, okay, well, what about the size of our Earth? Is that a good thing? I mean, you say the diameter, is that good? Would we want it to be bigger or smaller? What would be the effect of that? Well, actually, Earth needs to maintain a minimum mass. So it needs to maintain at least a certain size. It can't be smaller. Now, why does it need to maintain this? First, it needs to maintain this because this is how it retains an atmosphere. So we need an atmosphere surrounding our Earth so that we can have a free exchange of the chemicals of life. So we need to be able to exchange chemicals within the atmosphere to prevent them from escaping. But we also need to have the option of exchanging chemicals from space into our atmosphere as well, controlling what's going there. So the atmosphere kind of allows for this free exchange and kind of monitors it. Also, our atmosphere kind of provides a protection from cosmic radiation. So it kind of is like a little casing that protects us. Now, for life, not only do we need this atmosphere, but we actually need it to be an oxygen-rich atmosphere. Since human life, we need oxygen, and ours is a 20% oxygen-rich, which is the exact amount we need. Too low, we don't have enough oxygen, which is what can happen if you climb really high, you don't get enough oxygen, and then your body is affected by that. But if we have too much oxygen in our atmosphere, then fires would spontaneously occur and we wouldn't really have the environment that we need. What else do we need? We also need to keep the heat from the interior from being lost too quickly. So if it did not have the minimum mass that it needs, say it was smaller, then the heat from this interior would escape too quickly. So we need it to be big enough so it would kind of maintain that interior temperature. Obviously, some will escape, but we need it to be controlled. If the planet were smaller, then this heat would escape very quickly, and then our planet, the core would cool quickly and basically be dead, which is similar to what we expect happened on Mars. So we need a balance there. Now that's if the planet was a little smaller. Like what would happen if our planet didn't have this minimum mass? But let's talk about what would happen if the planet were more massive. What would that look like? So what if Earth were a little more massive than it already is? So if it were bigger, if the planet was bigger, then we would have a higher surface gravity. So the gravity that we would feel on the surface would be stronger. And so what would happen is the rocks at the base of mountains. So imagine a mountain, and if you're at the bottom of the mountain, you're going to feel a lot of pressure. You could kind of think about this if you've ever done one of those human pyramids, if you've done cheerleading, anything like that. If you're at the base, you're going to feel the pressure of the weight of those above you kind of pushing on you. So at the base, you need somebody really strong who can endure that pressure. However, in mountains, they can only have so much weight kind of pushing down on them. And so what happens is if we had a higher surface gravity, then that would push down on that base of the mountains, and the mountains would end up fracturing. They wouldn't be able to withstand that much weight. So higher gravity would actually pull down on the mountains, and we wouldn't have as high of mountains and as severe mountains. It would kind of just smooth out the surface, because it would pull on those mountains to kind of distribute that weight instead of it being in just kind of one location. It would smooth it out so the base wouldn't have as much weight kind of pushing down on it. So what would happen then if we have kind of a more flattened out surface? Well, as we know, the Earth has a lot of water in its crust. And so without mountains and continents, the water would just spread out and we would actually have a water world. You may have seen this movie at some point. And if it were all to spread out and we wouldn't have any mountains or continents, the water would actually end up being a depth of 2 kilometers or about 1.24 miles. So That would be a very different world than what we are expecting. So then the question is, well, isn't water what we need? We need water for life. Whenever people are looking out at other planets, it's always like, oh, do they have water? Because water is one of the essential elements for life. So if we just had even, if it's just a water world, would that be a bad thing? So let's look at that. Would a water world be good or would a water world be bad? So actually, a water world is not good for life. So one of the things that we need on life, for life to happen, is we need to have that balance. So life on Earth is due to a few things, but one of the things is this energy-rich, sunlit surface of the oceans. So we've got the oceans, they're getting energy from the sun, but then what they're also happening is they're getting nutrients. Remember I talked about how they're going to get different nutrients from the continents, from the land. So there you go on the land. And this is when we talk about the tides, and they'll get it. So they'll get the nutrients from two ways. One, the tides going in and out will pull those nutrients off the continents and into the oceans, and then also weathering. So weathering is when we have rain coming down. Rain will wash across the land, either down the mountain or whatever, and as it's washing down and going into a river or a lake or the ocean, it's going to collect different nutrients on its way. And so this is the way that we would get various nutrients from the continents into the oceans. And as these nutrients get into the oceans, this is what feeds the various organisms in the oceans. Now, if we had a water world, we wouldn't be getting these nutrients, at kind of a slow, steady rate. What we have would be there the entire time, and that would be all we would have. And if you have a lot of something, what would happen is it would actually sink to the bottom. So the way that you can think about this is actually called a supersaturated solution. And so if you've ever made, let's think, like maybe Kool-Aid or even hot cocoa. So let's go with hot cocoa. So you have your milk and you have your hot cocoa. And if you mix it in, it will dissolve. But if you keep mixing, what will happen is, and you keep adding more cocoa, you're going to hit the point where it's saturated. It cannot dissolve anymore. Now you can tweak it a little bit, heat it up, it'll dissolve a little bit more, but you're always going to eventually hit the point where it cannot dissolve anymore. And what happens is, if you keep adding it, it's just going to settle at the bottom. So if you've ever drank your hot cocoa and you see a bunch of cocoa powder sitting at the bottom, it's because you added too much from the beginning. So this is what would happen in a water world. All those nutrients that we would need would just float down to the bottom. Another thing that would be negative to a water world would be that the salt concentration in our oceans would be prohibitively high. We're okay with some salt, but it would be too high for life to exist. So right now, with our tides, the way that we kind of manage the salt in the ocean is that the tides will go in and then the tides will come out, and the ocean there has salt. Now, in certain parts of our continents, we have large kind of marshy areas along some of the coasts. So as the water goes in, because it's shallow, some of that water would be left, and because it's shallow, it'll get left and it will evaporate very quickly. And then it will leave salt right there on the land, on the coast. And then when the tide goes out, it will have left some of the salt there. And so this is a way to kind of balance the salt concentrations. So our salt deposits on the shallow coastlines kind of control the concentration of the ocean. But if we have a water world, we don't have that coastline anymore. So there's nowhere for us to be able to kind of go and deposit the salt if our concentration is too high. So what would happen? Just like with our cocoa, if we have too much salt, it's going to just settle at the bottom. So the salt will settle at the bottom of the ocean, and the ocean would then be a supersaturated solution. So then we would have just a too salty solution. So what we're seeing here is it's really important to have land. And so let's look at what are the other properties of just our land that helps. So we kind of looked at the water aspect of it, but what about the land itself? So there's a few things that are beneficial on our earth from just the land itself. Now, with the land, the Earth has plates. So underneath kind of the lithosphere, there are some plates, as they call it, that kind of are able to move around. And as they move around, this is called continental drift. So continental drift refers to the movement of a dozen or more massive plates in the Earth's lithosphere. So the lithosphere is that outer rigid shell of the planet. You can kind of see it a little bit in this graphic. Okay? And so this is one of the ways that we were able to get mountains. So these plates kind of moving around is one of the ways that we were able to form mountains, because as over time, as the mountains collide, they would form mountains. They can collide this way, or they can kind of go underneath or buckle. And so this is how we get the various different kind of land formations from these movements of these plates. But why would this be good? You might be thinking, okay, movement, we already talked about why mountains are good, but you also might be thinking, well, if the plates are moving, isn't that earthquakes as well? That doesn't seem very good. And besides having mountains, what else is it beneficial to have these plates, these plate tectonics? So plate tectonics is actually a central requirement for life. You might not be thinking, how does plate tectonics and the movement of these plates have to do with us having life on Earth? How is that helping us? Well, an interesting fact that plate tectonics is only found on Earth. No other planets or moons have plate tectonics. And the reason is because one of the main things you need, if you need these plates to be moving, you need some sort of lubricant, something that helps facilitate them for moving. And so in our case, we have oceans of water. So all of these oceans of water help lubricate and allow for this movement. So other places don't have water, so they don't have this kind of lubricant. Also, we said that earlier, the plate tectonics helps with the development of continents and mountains, which prevents a water world. So very important. We need water, but we also need water to be kind of maintained and not just be everywhere. Well, another thing that really helps through plate tectonics is actually plate tectonics drives the Earth's carbon dioxide rock cycle. So you may say, well, what is a carbon dioxide rock cycle and how does that actually help us? So let's talk about this. What is this carbon dioxide rock cycle? And I'll have a picture of it on the next slide just so you can see it a little bit better. So this cycle is actually really important because it regulates the environment. So in our environment, we have our atmosphere, and then you have the land, the surface, and in between the outer part of our atmosphere and the surface, we're going to have a lot of gases and a lot of stuff going on. But one of the things that's there in that part of our atmosphere, our lower atmosphere, are greenhouse gases. So what are greenhouse gases? What do they do? And so these greenhouse gases actually absorb infrared energy that's coming from our sun, comes through, it absorbs this energy, and it actually warms the planet. So if you've ever been to a greenhouse, greenhouses are usually pretty warm, feel kind of humid. So you can kind of think about it like that. So these gases that are right there in our atmosphere, they're absorbing this infrared energy and they warm up our planet. Now, this might sound really good. However, we need something that kind of balances this, because if we have too much greenhouse gases, then they're going to absorb too much energy and our planet would be too warm. And like I said before, we need a very delicate balance of our temperature on our surface for us to be able to have life, for us to survive. So plate tectonics actually helps this balance of these greenhouse gases and the temperature on our surface. So how does it do this? So plate tectonics cycles fragments of the Earth's crust down into the mantle. So the fragments that I'm going to be kind of focused on are limestone. So limestone is made of calcium, carbon dioxide, and oxygen. And carbon dioxide is a greenhouse gas. So these plate tectonics what it does is it's going to have fragments of the crust, that surface of our Earth, and it's going to push it down into the mantle. And I'll talk about on the next slide how that does. So what happens is these components of limestone, calcium carbon dioxide, and oxygen, we mainly want to focus on carbon dioxide, is going to get pushed down into the mantle of the Earth. And as it gets pushed down, the planet's internal heat, because remember we said that in the middle, as you continue into the center of the Earth, it's getting hotter and hotter. So that internal heat is going to release the carbon dioxide. And when it releases through volcanoes. So it's going to be vented back out into the atmosphere through volcanoes. And so this controls the surface temperature of the Earth. So if we have too much carbon dioxide, it will go into the Earth's crust, go into the mantle, and then if we need more, then it will be released out into the atmosphere through the volcanoes. So here we can kind of look at this rock cycle. And this picture has a few different aspects into it, all the different kind of things that we've already talked about. So here we want to focus on the fact that having mountains and having kind of this change and having higher elevations in our continent is very important so that we don't have a water world. But however, through weathering, and so that's when the water is going to be on the surface of the land and flow down into the oceans is very vital for the transport of different nutrients and minerals and elements into the ocean. So weathering and erosion, then we're going to have transport through either ice, water, or wind to get down here. Then we'll have deposition. So with lakes, streams, and swamps, this is where the salt will kind of go onto those lower surfaces on the coastline, and that will regulate our salt concentration. Okay. And then we're going to talk about the CO2. So what also happens here is one of the things that will be transferred into the oceans and down into is also CO2. And so as it is going to process through the rocks, through the plate tectonics, it will be going through into the mantle and be deposited. Then as it is in the mantle, and once it gets heated up, then it will come out of our volcanoes and be vented out. And then it will go back into the atmosphere. And this is kind of the cycle that we have that balances our CO2, which then thus also balances our temperature of our atmosphere. Now you might say, well, okay, well, but what drives this cycle? What is determining how much is getting vented and how much is not getting vented? And so what is actually driving the plate tectonics is that temperature, that heat from the core. So where is this heat coming from the core? It's actually coming from radioactive isotopes. So these radioactive isotopes that are found in the Earth's core are mainly potassium-40, uranium-235, uranium-238, and thorium-232. And these are located deep within the Earth's core. Now, where did these isotopes come from? So the way that we get heavy metals is through supernova. So as the stars live and then they die, when they die, they release heavier metals. And this is how we were able to get the production of planets and other bodies. So these heavier elements, these isotopes, were originally produced by supernovae. Now it's interesting that currently the supernova rate is declining with time. So at the very beginning, if you remember from my initial talk on the Big Bang, at the very beginning of the kind of life of our universe, we had a lot. Stars were being formed, stars were dying, lots of supernova, lots of things getting shot out into the atmosphere, heavier metals, then those are combining, and then more supernova, more stars, then those combine with the ones that are already there. And that's how we kind of built out from lighter, simpler elements to bigger ones. Now, as time has progressed, this rate of star death, this supernova rate, is actually declining with time. And so what happens is if you need these heavy elements, these isotopes, radioactive isotopes to be in the center of your planet, then if there's less of them, there's less likely that there's going to be Earth-like planets. It limits the production of Earth-like planets because this is the basis. This is a very important aspect of how our Earth is able to have life. So because we don't have as much production of these radioactive isotopes, then we can make the assumption that it's less likely that there would be Earth-like planets out there in existence. Also, if there were some planets that have some of these isotopes, they wouldn't have the same internal heat, and so their environments would also not be the same, and they would not be conducive to having life. So what else does this radioactive decay do in the center? So not only do these isotopes that have radioactive decay and producing heat in the center help with this plate tectonics and the venting and the whole CO2 rock cycle, it actually produces another very interesting aspect that helps with life. So this radioactive decay causes Earth to have a magnetic field. And so this magnetic field is produced by the radioactive decay that drives convection of the liquid iron that surrounds the Earth's core. So remember I said you've got the Earth core with iron and liquid iron around, and as there's heat and it's flowing and you have convection inside the middle, this is going to drive this magnetic field. So why would it be good to have this magnetic field? So this magnetic field around Earth, and this is the picture here kind of shows a little bit of what I will be describing. So this magnetic field actually helps life on Earth for several reasons. First, it shields from low energy cosmic rays. So any type of radiation that's coming in, the magnetic field shields from it, kind of blocks it from even getting into our atmosphere. It also protects and shields from solar wind particles. These solar wind particles would come in and they would strip away from the upper atmosphere. So they would go in and they would take the water that's in the upper atmosphere, they'd break it apart into hydrogen and oxygen, and we just remove the water that we have. So if they were allowed to do that too much, we would lose more water, which would then adjust and cause, issues with our temperature and our life on our planet. And so having this magnetic shield is a very unique thing that we have due to plate tectonics and due to our radioactive decay. All right, so what else protects the Earth? What other things is helpful? So another thing that really helps us and protects our Earth is called the Earth's albedo. And this is another natural thermostat. We already talked about one natural thermostat. So we talked about plate tectonics and how it balances those greenhouse gases. And so there's a cycle that doesn't allow those greenhouse gases from getting too high or too low. And so with either removing the CO2 from the atmosphere or putting CO2 back into the atmosphere, depending on if we're getting too hot or too low. Now, the Earth's albedo is another kind of way that our Earth determines how hot or cold our planet will be. So what is albedo? So albedo is the proportion of sunlight a planet reflects. So if you have a high albedo, that means you reflect a lot of sunlight. And if you have a low, that means that you're not reflecting as much. So what will actually reflect sunlight on our Earth? So a few examples of things that reflect sunlight are the oceans, polar ice caps, and even deserts. Even within the interior, deserts will. But not only that, but we also have different things that kind of help another natural cycle that will help keep this in balance. And so I want to just give you an example of one. So one example of something that helps to kind of control this albedo to help increase it or decrease it are very specific marine algae. So there's a specific type of marine algae that does dimethyl sulfide production. And so why is dimethyl sulfide important? So dimethyl sulfide helps to build what we call cloud condensation nuclei, CCN. And so cloud condensation nuclei are particles around which, when water is in the atmosphere, these particles, the water will condense around these particles to form clouds. Okay, so these CCN are in the atmosphere, the water will come around and form clouds. So what happens is, as the ocean temperatures start to get higher, it kick-starts these marine algae to start producing dimethyl sulfide. So ocean temperatures get higher. Oop, I need to create some dimethyl sulfide. So I create more dimethyl sulfide, which creates these cloud condensation nuclei that go up into the atmosphere. More water is going to go around them, and now I have more clouds. Well, clouds is a higher albedo. So the more clouds I have, the more light will be reflected. And if there's more light reflected, my ocean temperature will go down. And as it goes down, I will slowly reduce the production of that dimethyl sulfide. So you can see this is just a self-regulated cycle that kind of helps adjust the temperature of our surface. Just another thing that we are kind of learning about that kind of helps to really allow for life to exist on our planet. Now, I want to talk about one other aspect related to our moon and our planet and where we're located. That is kind of a special, unique little event. So we'll change gears just a tad. And I want to talk about solar eclipses. So a solar eclipse obviously is a very unique event. It doesn't happen very often, and a very special event. And what's interesting is, of the 9 planets in our solar system with more than 63 moons, the Earth's surface is the best place to observe an eclipse. So if we want to see a solar eclipse, Earth is the best place to see it. Now, I do want to note that you can also see a solar eclipse on one of Saturn's moons. Prometheus also helps with this. It comes close, but the issue with that one, why it's not a perfect solar eclipse like what we have with our moon on Earth, is that Prometheus is kind of like a potato shape. And so so the shape isn't perfect for the sun. And then also it's going to be a very short eclipse. It only lasts a few seconds, where we have a much longer eclipse. So really, our eclipse, we have the best eclipse. So why is a total eclipse even possible? What's interesting, because the sun is 400 times bigger, much, much bigger than the moon, and it's actually 400 times further away. So this kind of provides a perfect match and allows us to have that perfect solar eclipse. It's kind of interesting to note that the time and place where a perfect solar system would appear in the universe, the only place that you could be to have this kind of perfect solar system, is on Earth. And Earth is the only place that has observers to actually even enjoy or be able to see a solar eclipse. It's kind of an interesting thing to kind of think about. There's nobody else on any other planets, and there's no solar eclipses. So the solar eclipse happens just where people can actually observe them and measure them and enjoy them. So why are solar eclipses interesting or important? They've actually resulted in a lot of important discoveries. So by having the ability to observe these solar eclipses, we've actually been able to learn a lot about our universe. So the first thing that we've been able to learn about our universe from these is we've been able to learn about the nature of stars. So astronomers were able to use spectroscopes and look at the sun during these solar eclipses and be able to determine the color spectrum of the sun. And then they were able to do this also with distant stars and be able to compare the color spectrums and learn about the differences between stars and our sun and between different aspects and characteristics of them. But we were only able to do this and get this information through a solar eclipse. The next thing that we were able to get from a solar eclipse is that we were able to confirm the fact that gravity bends light. So an experiment was done in 1919, and this experiment was only possible during a total solar eclipse. And from this experiment, they were able to confirm that gravity bends light. And this was a very, very important part of Einstein's theory of relativity. And so once we were able to get that confirmation from that experiment, this led to general acceptance of Einstein's theory. Before that, it was accepted, but this kind of pushed it over and was like, oh yeah, 100% we accept this. And then the third thing we were able to do is we were actually able to calculate the change in Earth's rotation. And so being able to calculate when these solar eclipses were happening and where you were in relation to the Earth when the solar eclipse happened, we could actually adjust modern calendars to ancient calendars who recorded the solar eclipses over time. So then that was able to give us an idea of how our Earth's rotation was changing when we looked at our calendars and ancient calendars. So let's look at this. This is a kind of an interesting thing to kind of think about, that we're able to measure so many different things about our moon, our sun, our Earth, our solar system, our galaxy, and our universe, as we talked about in the previous lectures. And all of this measurability happens in the same place where it's habitable. And there seems to be a correlation between habitability and measurability. And there seems to be no real obvious reason to assume that the very same rare properties that allow for our existence would also provide the best overall setting to make discoveries around the world, to make discoveries of the world around us. So it's just kind of interesting that we are able to have life on our planet, but we're also located in the best place to learn and discover about the things that are around us. So let's conclude. We started this kind of 3-lecture series, little mini series, looking at Copernicus' principle and thinking about, is our solar system, our universe, and our planet just like everyone else? Is it not unique? Is it just mediocre? Or is it actually unique? So if we want to look at the existence of life, there's 3 possible reasons. There's some natural necessity, like the laws of physics, some reason that necessitates that it occurs. Random chance, well, if you create enough planets circling enough stars, then the odds say at least one of them will have life, which we kind of talked about throughout these lectures, that there's a lot of factors that would have to randomly happen for life to be able to exist in a very short amount of time. Or 3, life was created. Some believe that the universe was designed for observers living in places where they can make scientific discoveries. And so I leave it to you to determine, is our planet and where we live just chance and not unique? Or do we actually live in a very unique universe, solar system, and planet? All right, thank you very much for coming to my talk.